All right. The test was on sections 2-4. Let's use a hyphen so it's inside the book. 2-5. We did 2-6, 2-7 kind of together. I'll tell you what that would be on there, or the kind of question. 3-1 and 3-2. All right? So, 2-4 and 2-5 had to do with absolute value. We began looking at absolute value with equations, then inequalities, and then graphical solutions. 2-6, 2-7 had to do with the simple proofs, where we were able to give a reason for each statement along the way. 3-1 was looking at x and y in the same equation, or one equation with two variables, and looking at multiple solutions. And then 3-2 was graphing those, simply using either graphing by points, graphing by intercepts, graphing horizontal or vertical lines, or looking at like intersections and such.
Are there going to be a lot of problems in 2-6 and 2-7?
There'll be one. There'll be one proof. You'll have to give me the reasons. Okay? So it'll be similar to like the homework one. So where you're given all the statements on one side, and you have to fill in the reasons for each statement. So it's similar to the first test, the one we had on that. Okay? It'll be using the properties of equality. So additive property of equality, associative property of multiplication, identity property of addition. All right? I'm tempted to give you like a bank of options. So maybe you can just fill in the blank from that bank. Okay, I might give you like 15 options of choices for reasons, and you have to put the right reason in the right spot. Because I'm not really concerned about the wording. I'd really like to see what your thought process is. So by giving you those words ahead of time, at least I could see that you know where they should be. So associative means this, or commutative means that. All right, so you could expect that. So don't focus on like memorizing every single wording of all the reasons. Really focus on understanding what each reason means. Like what the associative property actually means. What the commutative property actually means. Okay, the wording of it, don't worry about it. I'll give you the wording on the test. Okay? Let's start with 2-4. 2-4 we began by looking at absolute value equalities. Equalities. A few of you were here this morning for this. Can somebody give me an example? Make up your own example that you want to work on. Ben, give me an example of an equality with an absolute value that was difficult, like this morning's, where we had a multiplier and something added to it on the side. That does not matter, whatever you want.
So like absolute value of 2x minus 4 and like plus 2 equals
Give me a positive number.
10.
Okay. And I'm going to put a 4 out in front to make it even tougher. Okay? Perfect. That looks good. So this was something like you had in the quiz. What is the goal? What do you need to do to solve anything with absolute values? You need to do something first. Niall. Isolate the absolute value. That's the key here. You have to isolate the absolute value. It's not isolated. That plus 2 is annoying me. That 4 in the front is annoying me. I've got to get rid of that stuff. So you need to think of this as following. You don't have to write this down, but think of this, okay? If this were the equation, what would you do to solve it? How would you solve this, Will? You'd subtract 2 to give this 8, and then how would you go to the 4, Will? So this is the same thing above. These are analogous. Just now you have an expression instead of just x. You solve the above one the exact same way. So, Will, go for it. Subtracting 2, what do we get in the next line?
4 and the absolute value of 2x minus 4 equals 12. Sorry, equals 8.
Okay, next line. Keep going.
Divide by 4.
Good. Giving me?
The absolute value of 2x minus 4 equals 2.
Good. All right, I gave Will enough of a headache there. How do I go from here? What do I do next? Paul, help me out with this part.
Now you would, you have to make 2 equations.
Very good.
One is going to be with -2 and the other is going to be +2.
Very good. Okay, again, one with a -2, one with a +2. And at this point, you're just solving them both. Solve them separately. In the first scenario, let's see, we add 4. Then we divide by 2. We're going to get x equals 3. Over here. Right, add 4 gives me 6. Divide by 2 gives me 3. Add 4 gives me 2. Divide by 2 gives me 1. So here are my 2 solutions. Okay, if you write this in solution set, it would look like this. Okay, it's not a coordinate because we're in the braces here. We're not in parentheses. The brace indicates the solution set. Does that make sense? Are there any questions on that specific problem? Okay. All right. Now, how would I know I'm right? How would I know I'm right? Nine.
You plug the x equals whatever back into the original column.
Exactly. Just plug in your solutions into the original. Please don't plug them in here and here, because if you made a mistake with your algebra and above, when you plug them in here, it'll check, it'll work. But because you made a mistake earlier, it's not right. So you need to always check in the original. Is that clear? That's the reason you check in the original. Because if you make a mistake and you check in a mistake, it'll show up as being correct. But this is not correct. You checked it in a mistake. So it wouldn't make sense in the end. So it's got to go back to that original statement. Okay? All right. Now, let's keep going with 2-4. The next thing with 2-4, inequality. Charles, give me an example. Doesn't matter. Make one up yourself completely.
2, 4 is x plus 4 is less than 10.
Absolute value, right? Absolute value is less than 10. That works. How would I solve this one? This is already isolated, agreed? So we don't have to do anything. But had it not been isolated, we need to do what we did in the last problem. We need to move the stuff around, but it's already isolated. Mike, what do you got?
So x plus 4 is less than 10,
Good.
and x plus 4 is greater than -10.
Good. Okay, so it's the same approach, but Mike remembered when you make a negative of one of them, you're really thinking about like you're multiplying by -1. It's the easy way to remember it if it helps. So make sure you go ahead and flip that sign. Now, solving this, how do I solve it? Simple, right? Kelly?
Subtract 4 from both sides.
All right. So I've got a statement that says x is less than 6. I've got another statement that says x is greater than -14. I can use the context clues to figure out if this is going to be an and or an or statement, or I can look at the original and think about if I've memorized what the less than symbol means versus the greater than symbol. What do I have here? Give me a reasoning as to what you think.
And because if x is less than 6 and x is greater than -14, when you put on an underline, then it would show what the two arrows facing each other.
Very good. Good explanation, Ryan. I like it. They overlap. This is what Ryan's saying right here. He's visualizing this. He's saying, well, less than 6 looks like this. Greater than -14 looks like that. They're going to overlap. And when you have that overlap of two sets, it's an and statement. All right? We also noticed in the beginning it was less than. Whenever it's less than, we remember it's and. So my actual solution set on the number line should really look like, and I'll shade it in blue. All right, there's my actual solution set on the number line. How do I write this as a solution set? Charles, what do you got?
So x equals -14 through 6.
Through 6. So less than x, less than 6. Okay, now, you can write it backwards, but some of you did in the quiz. It's not traditionally written that way. It doesn't really matter. I would never take off points for it, so you're not going to ever lose points for that. But I did write a note on some of your quizzes. If you write it with 6 and then a 14 over here, these need to be flipped. And you did that. But traditionally, you always write the lower bound and then the upper bound. Yeah, well.
For number 6, is it shaded in the circle?
It's not. Sorry, that's not shaded in. It's just
No.
not clear. Yeah, neither of them should be shaded in. Sorry, it's just the stylus got a little, funky. But yeah, neither of these are shaded in. Okay? It's an open circle because of why again, Will? Right here, right? Yeah. Exactly. All right, so that's my solution set. That's my graph on the number line. When a problem says state the solution set, you need to state it. Some of you on the quiz left that's the number line. That's great, and that's good. That was part of it. But you need to state the solution set also if it says that. All right, especially with the graphical solutions. I want to see the solution set because the graphical part is not much work. Okay, I want to see the actual solution set. When you're doing the graphical stuff, I'd really like to see things like starting point, deviation, like list what you're doing so I know on your graph what you've gotten, because anybody can solve algebraically and then just draw the graph and maybe just do solve algebraically in their head. But when it says graphically solve, that's what we're going to see in this next example. So let's be a greater than or equal to. Aside from that, I don't really care too much. So give me some variables or some examples here. Kelly, what do you got? Make one up.
4 times the absolute value of x minus 2 is greater than or equal to 12.
All right, perfect. Okay, so that 4 is on the outside there. How do I get rid of that 4 to start? I don't want it there. I want to get rid of it.
Divide everything by 4.
Divide it by 4. Hey, let's make this a little tougher. Put a little 2 in here. Just to make it a tiny bit tougher. Put a little 2 inside. All right, so I got rid of that 4, which is great. Now I want to get rid of that 2 that's there. How do I get rid of that 2? This little red 2 that's in there. Well, divide everything by 2. Okay, either divide everything by 2 or factor out the 2. It doesn't matter either way. You can go ahead and do this. All right, you could factor out the 2 like that, take it out of both of these terms, then divide by 2. Or as Will said, just divide by 2 in the whole equation. In the end of the day, you're going to end up with the following. 3 divided by 2 is 1.5. And I'm using decimals only here. I usually leave things as fractions, to be honest. But because this is my deviation, I want to know what it physically means. 3 over 2 is not always obvious what it means. If I write it as a decimal, I know how far I'm going to move left and right on my graph. Okay? So that's what I'm left with. X minus 1 is greater than or equal to 1.5. What is the next step in this process? Right.
You have the 2 equations.
Okay.
The x minus 1 in the absolute value, and then it's greater than or equal to 1.5, and then that is less than the first one.
Graphically, though, if we're doing graphical method, that's algebraic, you're right. So Ryan answered, like, if it's algebraic, break it up, right? And separate it. What if it's graphically solving? How do I do that? Do you remember? Think back to this morning. We did an example. You were there with starting point and deviation.
Yeah, -1 to each side.
Yeah, this would be, now be careful. It's always, if we look at our standard form, the starting point is always some quantity like C, we'll call it. It's always minus. So 1 would be the starting point. Remember, this minus here has always got to be here. Whatever this number is what the starting point is. So 1 is the starting point. Good. Keep going, right?
Then it would be plus 1.5, or 1.5 to the right, or 1.5 to
Yeah, so go 1.5 to the left and right. 1.5 to the right, Paul. What do I get 1.5 to the right?
2.5.
Good. Niall, 1.5 to the left. What do I get?
Negative, or, yeah, negative 3.5.
Not 3.5.
Oh, 2.5.
Be careful. You're at 1. You're taking away 1.5.
Negative 0.5.
There it is. Okay, those are those quantities that we can identify. Again, this is my starting point. This is my deviation. Remember that the format should always look like this. Okay, x minus some number is greater than or less than or whatever it is, some number. It's always a minus. So had this been a plus 1, how would you rewrite it? If it had been x plus 1, Luca, how would I rewrite that?
X plus 1, then it would be x minus negative 1.
And it would make -1 the starting point now. So even if you have a positive, make it a double negative to remind yourself that you're really looking at this quantity, whatever is here, not this sign. Make that a minus. If this were a plus, make it a minus and make that a minus, and you get minus a negative, which really means plus.
If you're having a double negative, wouldn't it be like now the starting point would be negative?
Now the starting point would be negative, exactly. When you have the double negative, the starting point is negative. When you have the single negative here, or the minus, the starting point is whatever this value is, not this. Okay? Good point to note there, Paul. All right, the last part is we have to actually figure out where we're shading, right? So we can do this more than one way. One way to do it is just to test points. If I take the number 1, or even the number, let's say the number 0, I'm testing. So I have 3 regions. This is one region. Let me point with the marker, hold on. This is one region from here over. This is another region, and the middle is another region. Ignore this little hash mark, although we put it there because we're indicating our starting point. Okay, so we have 3 regions. You could test points in your original statement, and if that statement turns out to be true, it means you shade that region. Or you could just simply look. And let me describe what this means, so stay with me here. If you go back to our beginning definition of absolute value, this really means the distance from 1. This means if I were to read this in English, I would say the following. The distance from 1 is greater than or equal to 1.5. That's where my solutions are. They're more than a unit and a half away from 1. So here's 1. This is like a half a unit away. This is 1 unit away. This is exactly 1.5 units away. This is 2 units away, 3 units away, 4 units away. We want the distance away to be more than 1.5. So we want it to be out here somewhere. So we could start by just simply doing this and shading to the right. Because again, we want the distance, this physically means distance. We want the distance from 1 to be more than 1.5 units. This is 1.5 units. The distance more than that is everything this way. Now, I could also go to the other side. I could say, ready? Starting here, I'm right on 1. Then I'm a half a unit away. Then I'm a full unit away. Then I'm 1.5 units away. Everything beyond this is more than 1.5 units away. And this tells me more than 1.5 units. That's what it says. Greater than or equal to 1.5 units. So I'm also going to shade in over here. Alright? Now, the other reason we can know this, when you see a greater than, you think of or. The last example we did was a less than, we thought of and. Okay? So if you remember that, that's fine as well. So to solve a problem like this graphically, please isolate the absolute value, whatever you have to do that first. Write it in this form with a minus. If it's a plus, make it a minus a negative. Identify your starting point. Identify your endpoints from your deviation. And then shade accordingly. What would the solution set for this one look like? What would it be here? Sabine, help me out with the solution set for this one.
Negative 0.5 is greater than or equal to x.
Okay, now do me a favor. It's going to be an or statement, right? Not an and. So let's write them as separate things with x first. So start with x. So x is...
X is smaller than or equal to -0.5.
Good. Or...
X is greater than or equal to 2.
Very good. Okay, please try and do it with x on the left. It makes more sense to make a statement that way. It's difficult to say to somebody, well, negative 0.5 is greater than or equal to x. Well, then you have to think about, okay, that means that x is smaller than that. So in the end, you're reversing your head anyhow. So please, start when you're writing more statements, make sure your x is on the left side. It just makes more sense logically. When you get older, if you're working in engineering, and this is really important for engineering, musical constraints. You have tons of constraints, material constraints, area constraints, monetary constraints, like budgetary time constraints. It doesn't make sense to say like, hey, for this project, you're going to have, it would make sense actually to say it this way. For the project coming up, you're going to have, at most 3 days to do it. So you have t is less than or equal to 3. It can be something less than 3 or 3, but nothing more than that. It wouldn't make sense to say 3 is greater than or equal to t. Because then you're reading it and you have to reverse in your mind anyhow. So start writing it this way with x on the left when you do that. Okay? It's not about me trying to tell you to do things one way. I don't want you to think that I'm like that kind of teacher that says, you can't have it this way. Because it is right technically the other way. And I would never dock points for it. But I'm trying to make you make more sense. Later in life, if you're in calculus class and you make a statement the other way, it's not going to make much sense. People are like, why would you say that? It doesn't make sense to do that. Like in English, how could I give an analogy in English to this? What's something that wouldn't make sense to do even though it's technically correct?
I guess depending on language, if you switch the words backwards, so instead of saying I'm going to my friend's house, I go to.
Yeah, technically speaking, that might be correct in English, I don't even know, but it wouldn't make sense to say it that way, as Will's saying, right? It wouldn't make sense to switch them around. I'm trying to think of another example, I can't, I'm not an English teacher. But mathematically speaking, you want the x on the left-hand side, okay? Just like a moment ago, when you have an and statement, usually it's the lower number and then the larger number on the right side. All right, so that's 2, 4, and 2, 5. That's really the gist of those two sections, okay? 2, 6, and 2, 7. Kind of example for 2, 6, and 2, 7 to look at. Let's say, I don't No. Show that if AC equals BC, then A equals B. Okay, that would be the statement that's the beginning. I would give you a bunch of statements, and you'd have to fill in the reasons for it. What's the first statement always going to be?
Given.
Yeah, it's going to be the given, okay? That's the first statement. AC is equal to BC, and the reason is always going to be given. You're not going to have to write given. No offense, I'm not going to give you a point if you just write the word given. I'm going to write given for the first step, so you won't fill it in. You'll fill in the steps afterward, okay? So let's say in this proof, the second step is to say that, let's see. Well, it would probably say 1 over C is a real number. Okay, and that'll also be given. There's no reasoning for that. Okay, you could say property of reciprocals or reciprocal property, because if the original number C is real, then the other one is going to be also. Now, what would the next step most likely be for statements? Can anybody guess what the statement would be? I'm not going to ask you to do this in the test. I'm just trying to make you think outside the box. What do you think the next statement would be? Good, Luca. Very good. Okay. Now, that would definitely be the next statement. You have to fill in the reason for this. Why can you multiply both sides of the equation by 1 over C? What property says you can multiply, hint, both sides by the same thing?
So, property of equality.
Yeah, the multiplicative property of equality. Why is it of equality? Because this is an equation. It's still equal, and it's multiplying. Had I added something to both sides, it would be then additive property of equality, right? Instead of multiplicative property of equality. So this is the multiplicative property of equality. All right, on the next line, it would look like this. Tell me in this case, Paul, how come I can change my parentheses when I'm looking at this? What property tells me I can change the order of parentheses? Associative. Of multiplication or addition?
Multiplication.
Yeah, just look at the problem, right? Multiplication, very good. All right, now, from step 4 to step 5, I'll probably see this now. What tells me that I can replace C times 1 over C with 1? With 1. Be careful here. It's not identity. I know, that's the one you want to think. I saw your hand jump up. Hold off on that.
Property of reciprocals.
Yeah, reciprocal properties. Remember, we're not actually using the identity property yet. We're just saying when 2 reciprocals are multiplied, we get 1. That's not the identity property. The identity property we'll talk about in a moment. Charles?
Could you say the prop of operative mult?
Of what?
Prop of operative multiplication?
Of opposites? No, because they're not opposites. They're either inverses or reciprocals. Either word is fine, but opposites in math indicate a negative sign. Okay? So you could use reciprocal or you could use inverse. Either word's cool. Okay, but if you're going to use opposite, we want to think about negative signs. Hey Ben, how about the last one now? If I have A equals B now, what property would that be?
Equality.
Something of equality, yeah, absolutely.
Commutative?
Commutative means I'm switching the order, right? Commutative, I'm switching the order. I didn't switch the order. It would say if this said 1A equals 1B, then it'd be commutative, right? Associative means I'm moving them around. This line here, the value of A has not changed. The value of B has not changed. So I would say that those values are identical.
Oh, identity.
So identity, okay? Identity property. Of multiplication, really, okay, if we're using the right terms here. It's an equality property, but it's of multiplication. So again, from line 5 to line 6 is what we're looking at there. Any questions on this? Yeah, Charles.
Well, they did the sum in the homework where they split it up into two things, like if this is true, do it, and then.
I won't give you two cases. I know what you're talking about. It was case 1 and case 2. That was that one example where it was like, I think, a squared in the example in the book, and then there was one in the homework. It was just if you had a certain case and then another one. I'll tell you now to be one line of them. So if that kind of confused you a little bit, don't worry about it right now. It's more important that you understand what properties go with what operations than splitting into two cases. I do know the example you're talking about, though. Okay? Any other questions on this? I think one of the major things that people were confused on in section 1.8 or 1.7 when we did this last chapter, the same idea was physically what step is what. So like from here to here, right? From 2 to 3 is that reason. Again, from step 2 to step 3, I multiplied both sides by 1 over c. I can see that that's the change. I multiplied by 1 over c, so that's the reason for that. Then, I changed the parentheses from here to here. That's the reason there. So the reason always comes after the line of the operation you performed. Then from here to here, we saw that the reciprocals were multiplying, giving us 1. So the reason for that was the property of reciprocals. Then we saw that anything times 1 was itself. The reason we can write this from this is because of the identity property of multiplication. Okay, so your reason is always after the fact. Some of you literally had your answers shifted up one, each of these. Like they were in the wrong statement line. You follow what I'm saying? Okay, it's always after what happens. So just think to yourself, from line 5 to 6, what happened? And then write that reason in line 6. From line 4 to 5, what happened? Write that reason in line 5. Okay, that's how you're approaching these problems. And that's one of the mistakes I've seen on like 3 or 4 people's old tests and even the quiz that we had on this. Okay? All right, that's 2.6 and 2.7. 3.1. I'm going to quickly look at 3.1 because this was like the really easy one except for the word problem. Easy because you're just trying numbers for them. So let's say for a word problem, okay? We'll do a word problem so we can get both things done at once. Let's say it says the following. Let's say that every time you sell, say you work at a hardware store, okay? You work at a hardware store that only sells 2 items. Doesn't make sense, obviously. Hardware is millions of items. Say you only sell 2 items. You sell PVC piping and metal piping. So that plastic piping and then metal piping. Okay? And PVC piping costs $3 per pipe. We'll say that they're standard lengths, 10 feet or whatever. Okay, for PVC piping. And for metal piping, it's $2 per pipe. And I tell you that, or $4 or whatever number, right? You can make up a million of these problems. I tell you that at the end of the day, how much money did you make today, Niall? Give me a number between 0 and 30. 15? All right, so you made $15 today. Niall made a total of $15 in sales. If I wanted to write an equation that represents this, which you're going to have to do, you need to solve these algebraically and then come up with all the possibilities of the numbers of PVC and metal pipes you could have sold for this to happen. What would that equation look like? What would that equation look like? Ben?
3x plus 2y equals 15.
Where x is?
3.
No, x is what? Like your let statement. Let x represent
The plastics.
plastic pipes and let y represent
Metal.
the number of metal pipes sold. Does that make sense? So you start with a let statement. I didn't write that there, but please start with that. Let x equal the number of PVC pipes sold. Let y equal the number of metal pipes sold. Next, if I want to find all the possibilities, what do I do to find all the possibilities here? Thank you. What do I do to find all the possibilities for x and y? Make a?
Do you make the y-intercept and x equals 0?
Well, that would be the graph, right? If you wanted to show a graph of it and see on the table to find a graph, we could do that, but we're not graphing this. I just want to see all the possibilities that x and y can take on. Niall?
Just making an XY chart.
Yeah, make an XY table. Okay, whenever you're asked to find all possibilities of answers, it means there's multiple answers. Now, in real life, you could sell half a PVC pipe, you just cut it in half. But hardware stores, traditionally, you have to buy the whole thing. You cut it in half on your own. So let's say you can only buy individual pipe lengths. Right? So like if you were selling, I don't know, board games, you can only sell a whole game of Monopoly. You can't sell half the game. So if I let x equal 0, what does y turn into? Let x equal 0. Just cover it up. cover this up in your mind. What does this become if I solve for y? Y is? Sabine? 7.5. Can I sell 7.5 metal pipes?
No.
So this is not one of my answers possible. You follow what I'm doing right now? Then I'd say let x equal 1. So I pick integers for x, and I see what I get for y. Because I know x has to be an integer. If y doesn't turn out to be an integer, then I can stop. All right, if x is 1, that makes this 3. Subtracting gives me a y of 6. That's a possibility. Well, when x is 2 now, I get 6 from 15 is 9. I get 4.5. Doesn't work. And some of you can pick up on the trend. What is y going down by? Every time x goes up by 1, what does y go down by?
1.5.
1.5. So the next one's definitely going to be 3, then 1.5, and then 0. So this works, this doesn't work, this works. Okay, now, one way to make this easier on yourself is to solve the original equation up top for y. So you don't have to keep doing this over and over again. Solve it for y if you'd like to, like this. It would become 15 minus 3x over 2. If I were to solve that for y, subtract 3x, divide by 2. That's the generic solution for y. I could then easily plug in these x's and come up with an answer much quicker than solving it over and over and over again. This is how you save time. For those of you that ran out of time in your last test or struggled with time, this is how you save time. You don't fill in that equation up top 5 times with x and solve it 5 different times. Solve it once and then just substitute in for x 5 times. Or plug it into y1 in your calculator and just go to your table and see what the table values give you. You don't have to do the work. Okay, make it easier for yourself, please. So the answer here would be these 3 possibilities. So you have 1 PVC and 6 metal, or 3 PVC and 3 metal, or 5 PVC and no metal pipes. Does that make sense? That's my verbal statement at the end of the problem. Okay, that's section 3.1 really. Okay? The other thing we did in section 3.1 is I gave you like a limited domain. I said the domain of x is like 2, 4, and 8. Come up with the possible solutions. Just plug those 3 into the equation and come up with the y values. But please list your answers as ordered pairs. So if I were listing these as ordered pairs, my solution would look like this. Okay? Now this is a word problem, so I'd write a solution out. But hypothetically, if this were not a word problem, if it were a problem where I gave you the x of 1, 3, and 5 and said find the y's, you would literally just write it like that. Okay? We have 1 minute left. I want to quickly discuss what was in 3.2. We did it yesterday, so 3.2 should be fresh in your mind. We talked about graphing lines by plotting points. I'm not going to make that an example on the test. I'm telling you now. You should always be able to do that. Plotting by intercepts, to find the x-intercept, set y equal to 0. To find the y-intercept, set x equal to 0. Then, horizontal and vertical lines. The horizontal line is y equals some number. The vertical line is x equals some number. And then the last thing I did was, I gave you a point. I said, if this point is on the line, find k. Remember to plug that point in to find k. And then I think the last one we did was something where 2 lines intersect and find that solution of the intersection. Okay? Practice all those types of problems from 3.2. All right? Again, this is not until Friday, so if you need help, you want to see me tomorrow, please try and find me at some point tomorrow during the day. Have a good day, guys.
Ready for the game, Mr. Howell?
Ready as I can be, always. How we doing homework today? Hey, Mike.
Everybody handed it.
That's all right. It's all right. Thank you. At some point, I just wanted to chat with you real quick. Nothing bad. I just wanted to. If you have class right now, everybody hand it in. Thank you. You're free? Oh, perfect. All right, give me a second. Let me just log out of here. I just wanted to talk about time management and stuff. I was emailing with your mom and I spoke with her at parent-teacher conferences on Monday. Okay, so just give me a sec. Okay.